Hey, Darren Turner's with us.
Good morning.
Good morning.
Hey, by the way, did you happen to get my email?
Oh gosh, what was it about? Refresh my memory, Darren.
It was late Sunday. It was I just wanted to talk to you about something. Um, do you have possibly have time after class today? It's just a little something.
Uh,
Or do you have a class right after this?
is there anybody else on here? Yeah, we got other people listening in right now. Uh, I'll try to sneak you in, or maybe I could read my email. That'd be good. Uh, but see, I've got to go see my grandkid.
Oh, I see. All right.
But no, no, you're important too. Uh, what's it pertaining to?
Exam 3.
Oh, okay. Well, was exam three the one that I made a mistake on and changed the key? I don't remember.
Um, no, it was regarding something that it was my mistake that happened on exam 3.
Uh-huh. Exam three. Let me see if I can find it here.
It was the one that was due last Friday.
Yeah. Uh, yeah. Now, here's the problem, Darren. I don't have a grade for you,
Mm-hmm.
but you turned it in.
Well, that's what I wanted to talk with you about. There seems to, well,
Yeah. Well, I'll look and see on my email there if it's turned in by the date. I can count it, but if it's not, I don't think I can help you much on that.
I know. I wanted to. We'll just talk with you a little bit, but
Yeah,
if you don't have time, that's more than okay.
I would love to talk to you about it. Okay, well, let's see. We got a pretty good crowd here, but I want all of you to do well. See, it bothers me if, uh, see, Darren, you got two good grades on your other tests. Oh, yeah, okay, I understand. We'll talk. Yeah, we got a good crowd. We have Mohammed, Darren, Ben, Seaman, and Ashley so far. And any of you have a question? Well, nobody has a question. Last time we seems like we were working on F82. So I want to talk about that briefly. And then today I want to talk about Moore's circle of stress, if we could get into that topic. Yeah, we'll get into that. But first we're gonna, unless you have a quick question, we're gonna talk about problem. I think it's F8-2. So let's get that. Let me find that. Here it is. It's on page 430 in your book, and they've got a cantilever beam. I think we started on this the other day, but we run out of time. And we have a 400 kilonewton force going down here. I'll put that in red. 400 kilonewton force. And see, they want us to section it right here. Section AA 0.5 meters. Well, why don't we just look at this section separately? Here, I'll move it over here someplace, and we can look at it. I've removed that section there, and here's your 400 kilonewtons. Can you see that you'll have to have a 400 kilonewtons? Actually, it's a shear force, isn't it? Going up, because we know the sum of the forces have to be 0 in this class. But see, now we got another problem. This thing will start spinning clockwise, so you got to have a counterclockwise bending moment. And you can figure out what it is. If this distance is 0.5 meters, take 0.5 meters times 400 kilonewtons, and what you'll get is 200 kilonewton meter bending moment counterclockwise. But we really like to look at left-hand members. So let's go back over here, and let me just erase that in there and put the forces on section AA on my left-hand member. See that 400 going up on the right-hand member? Well, there has to be a 400 going down on the left-hand member. Newton's third law says so. Newton's third law says for every action, there's an equal and opposite reaction. So, you know where that 400 kilonewtons coming from on that right-hand member? It's coming from the left-hand member. And where is this 400 kilonewton shear force on the left-hand member coming from? Well, it's coming from the right-hand member. Equal and opposite. And you see that bending moment, that counterclockwise bending moment on the right-hand member? Well, there's going to be a clockwise bending moment of 200 kilonewton meters on the left-hand member. Newton's third law. Here I'll demonstrate. I've got my hands here now, and I'm going to clap them. Are you ready? Here we go. Ready, get set. Ow, that hurt. Both hands hurt. This hand stings because this hand hit it. This hand stings because this hand hit it. They're equal and opposite forces, Newton's third law. I'm sure you knew all that. All right, well, now let's figure out, they want us to find the stresses. Now this is a beam, and it's a rectangular beam. I'll try to draw it here. Oh, gee. Not very good at drawing that stuff. There we go, here. Let me draw a larger, they said it's 100 by 300 millimeters. Okay, there's 100, 200, That's about right. There's 100. 100. 200. There we go. I could have measured it and been right on the money. See, this is your cross section. Here, I'll kind of draw it there so you can see it. They want us to find the stresses right there. This distance is 0.1 meter, 0.1 meter. From here to here is 0.2 meters, 0.1 meter. From here to here is 0.2 meters. And from there to there is 0.1 meter. This is all on page 430. And they want the stresses right there. They call it position A, point A on the cross section. They want the stresses there. Well, we have the equations. We know how they go. This one goes like this. That's our flexure formula.
Mr. Griffin?
Yes.
I think instead of that 0.2 meter, it's 0.3 meter.
Well, Mohammed, it's 0.2 meters from here to here, but you're right. It's 0.3 meters from the very bottom to the very top. But see, it's
Okay.
Are you okay now, Mohammed?
Yeah, I got it now.
Yeah,
I
it's
got it.
0.1 meter to here, 0.2 meters to there, a
Okay.
total of 0.3 meters.
Okay, I got it. Thank you.
Yeah, thank you for speaking up. But unfortunately, you don't get a thank you point this time.
Oh no, I was actually confused. That's why I asked you.
Keep trying for those thank you
Okay.
points.
Okay.
Yeah, very good. Okay. Now this is the flexure formula. Now this is going to turn out to be compression. Now the reason is because of this external force here. This beam bends down. Now I'll kind of fake it here, but I'm sort of exaggerating here. You understand? The beam, it's not going to bend down that much. But it will bend down. Now, we're used to having beams that bend like that, remember? And the beams that we've been studying, of course, again, I'm exaggerating, they have compression on the top and tension on the bottom, the beams that we've been studying. But now this beam here is going to have tension on the top and compression on the bottom. Are you okay with that? So see, everything below the centroid of this beam will be compression. So this normal stress that we're talking about, it's going to be going that way. It's going to be pushing. See, compression pushes. Okay, well, here we can get the amount. First, though, I need this moment of inertia. And for a rectangle, we all know what that is. It's 1/12 the base times the height cubed. Okay, go ahead and get that for me. And I'll ask one of you what you got in just a minute. Okay, I think I got the the moment of inertia, but let me ask my my students here. We'll pick on Samuel. Unmute and say hello, please.
Good morning.
Good morning. What'd you get for this moment of inertia for this rectangular beam here, Samuel?
I got 2.25 times 10 to the negative 4 meters to the fourth.
Good going. That's what I got. Okay, now look at here. We know the moment of inertia. We know the bending moment. It's 200 kilonewton meters. Now, y, that's always the distance from the centroid. Now, here's the centroid in the middle, right? And that distance there is 0.05. So here's my numbers. I've got 2.25 times 10 to the minus fourth. I've got 0.05. No, I put that in the wrong place. Let me get this right now. I've got 200 kilonewton meters, and this in the denominator is 2.25, 10 to the minus fourth. Yeah, I think that's right. Okay, and we know it's compression. See, that's what the minus, well, that minus doesn't work good this time because, see, the y is minus, really. And so you have a minus minus, that makes a plus. But that only applies to these kind of beams like this. That gives you tension on the bottom of the beam. Well, we don't have tension on the bottom, we have compression. So that minus, just don't worry about it, okay? That's for a typical beam, not a cantilever beam. All right, do that. I'm gonna do it, you tell me what you get. Here goes. Now I got an answer. I got 44.4 megapascals. If you got that, say uh-huh.
Uh-huh.
I need another uh-huh.
I got it.
Yeah, there's one. I need one more.
That's what I got.
I think we did good on that. Now, let's get the shear stress. See, I needed to mark the shear on here. We know what the shear is. It's 400. It's 400 kilonewtons. That's the shear. Now the bending moment's kind of hard to put on there. The book likes to draw that little squiggle kind of clockwise like that. A lot of times I'll do a bending moment with a double arrowhead like that. But see, the bending moment is 200 kilonewton meters. Okay, but now let's do the shear stress. Here we go. Shear stress is equal to now V is that's the 400 kilonewtons. 400 kilonewtons. And we got to figure out what the Q thing is. Now I, that's the 2.25, 10 to the minus 4 meters to the fourth. T, that's just the thickness, it's 0.1 meters. If we could only figure out this value for Q, we could get the shear stress. That's Remember, stress is what this class is all about. All right, well, let's see if I can make some room up here. We'll figure what this Q is. Need some room there to do it. Remember what Q is. It's the sum of the YI is what it amounts to. Okay, and there's a method for finding it. What you do is, if you want the shear stress at this location, you draw a line through there. There, I drew a line. And then what you do is you color the stuff above the line. Now we could do that. Here, I'll color it. I'm going to color all this stuff above the line. Yeah, I don't know if this shows up on your page there. There we go. I colored all that. And then what you do is you take that area, which is, well, the area is 0.1 times 0.2. But see this Y here, what that is that's the distance from the centroid of the whole thing, which is right here, to the center of this area, which is right here. Now I'm going to have to think about that. The center of that area, I think it's 0.05. I think this distance that we want here, I'm not sure about it. Now let me think about this now. I want to go from the middle of the whole rectangular area to the middle of this and yeah, I think it's 0.05. So what we got is 0.05. Come on now, right. 0.05 times 0.1 times 0.2. Well, I can do that on my calculator. I can't do it in my head though. That's too hard. 0.05 times 0.1 times 0.2. I'm getting 0.001. But maybe that's right. The units would be meters cubed. But let's check it. Now there's another way to check it. I don't know if I ever told you guys this, but you can color the stuff below the line and it works just as well. Here, let me do that. We're going to color the stuff below the line. Here we go. Ready? I'm coloring everything below the line. And so Q, the first moment of area, it's the same formula, it's just I'm going below the line, is equal to that area times this distance from the center of the whole thing down to the center of that area. It's this distance here. It's getting kind of messy here. But you know what? I think that's 0.1. So what we got is 0.1 times that area, which is 0.1 times 0.1. And if you do that, boy, Juve, I think you come out with the same answer. How about that? It doesn't matter whether you go above the line or below the line. And now look, we got everything we need. We know the shear force is 400. We know Q is 0.001. We got the I, 2.25, 10 to the minus 4. We got the thickness, 0.1. Hey, we can plug that into it. Go ahead, plug that in and get the shear stress for me. On your mark, get set, go. Well, I got an answer for the shear stress. I got 17.77 megapascal. Now, if you got 17.77 megapascal, say uh-huh.
Uh-huh.
Anybody else?
Mm-hmm.
There's two of us. There's anybody else?
Uh-huh.
Yeah, I think we got it right. So now we have the shear stress. Now let's draw the shear stress. Let's draw the stress element. I just need a little room here. We'll make some room. Now what we're doing here is, remember we had this beam here. We're making a little teeny tiny shear stress element, they call it. Here, I'll draw it kind of a little bigger here so you can see. Actually, it's a three-dimensional, kind of like a sugar cube. You ever seen sugar cubes? Some people put them in their coffee. But see, we have a normal stress, a compressive normal stress, and we know what it is. It's equal to oh yeah, it's the 44.4 megapascal. Compressive. Of course, now it's pushing on the back of that, you know, some of the forces are always equal in this class. And then you have a shear stress going down, and the shear stress is the 17.77 megapascal. A lot of times they'll just draw a kind of a side view of that stress element. They call it planar stress. Here, let me draw that for you. They'll draw a kind of a side view, and they'll have the normal stress doing this, and then the shear stress on this particular one is doing that. Now I didn't draw. Yeah, I did. I drew that on the backside. See, they kind of turned this around. You understand? It was like this, and we just no. I'm no good with 3 dimensions. I'm not explaining this very good. But you can see it's got compression, normal stress. I think you understand that okay. Come on. But see, you have some shear stress. Well, now we got a problem here. You can't just have some this one force going down, so you got to have a force going up. A shear stress going up. Well, now it's going to spin clockwise. To keep it from spinning clockwise, we're going to have these are all the same. They're all the same shear stress, okay? So there's your I think what you're doing is you're looking at it from over here. Here we'll put our observer right here. Here's our observer, and he's looking at this give him a sort of a crew cut here. Yes, see, here's our observer. He's looking at that stress element, and this is what he sees. Now, there is no normal stress in the vertical, but there could be. You could have a normal stress, a compressive normal stress doing that. That's possible. Or it could be tensile. If it's a tensile normal stress, then tension pulls, compression pushes. But in general, you could have a stress element that looked like that. They call this a stress element. Now, how do we get it? We started with the free body diagram, and we solved for all the red stuff on it. We solved for forces and moments on the free body diagram. And then we used our equations. What was it? The flexure formula and in this case, we used the flexure formula and the shear formula is what we did. And we found the normal stress and the shear stress. Yeah, you can see that. Maybe. There's sort of a procedure that we follow. You draw the free body diagram, you solve for all of the missing forces and moments, put a little comma there for the English instructors, and then you use your formulas. Now, it might be you're going to have to use some other formulas. We've discovered there's also pressure vessels. If you had a pressure vessel, you can have stress because of the pressure vessel. We've gone through a lot of different equations. And you use your equations. See, these are the equations you use. And you find the stresses. And then the last step, do I have room? Yeah, is you make a stress element. See our stress element? That's our stress element. You follow this step-by-step plan, and you've done it. I know you've done all of these steps here. It's just maybe we haven't majored on doing the stress element. But that's what we're going to talk about today. And we're going to show you more circle of stress, which is an interesting way of finding the maximum stresses in your piece. Do we have any questions on anything at all? Go ahead, I'm listening. Okay. Let's look and see how we did. Go to the back and then let's look. Let's look at fundamental problem 8.2. I'm looking it up now. Fundamental problem 8.2. They go through all of this stuff, and when they get through, they draw the stress element. And here's what the book has. The book says your stress element looks like this. hey, you know what? That's what we got. That's the same thing. They rounded off. We got 17.77. But yeah, hey, we did a good job, didn't we? Any questions on what we've done so far? All right, well, turn to page 450. We're going to be on page 450. Page 450. And they've got a stress element there. Now on theirs, they have some tensile stress in the y direction. They call it sigma y. And they have some tensile stress in the x direction. They call it sigma x. This is sort of a general, what you might encounter at the end of solving all those equations. And they have a shear stress acting on your stress element. And they call that tau xy. Now what they're doing on these two pages here, page 450, page 451, is they want to find the maximum stress in your piece. And what they're doing is they're looking at different angles. What if you looked inside the piece, rotate a tiny angle here, and looked at a stress element at an angle inside your piece? You see, we rotated it. We rotated that an angle, what do they call the angle? Theta. Okay, there you go. We rotated it, and if you did that, there'd probably be stresses on that rotated stress element. And what they did was they put normal stresses and normal stresses, but they called that sigma x prime, and they call this one here sigma y prime. Well, I don't see that they wrote that, but that's what they call it. And then you could very well have some shear stresses in here, and they call that tau x prime y prime. And they did a calculation. It's clever the way they did that. You could follow through their derivation, and I would love to have time to do that with you. See, what they did was this. If you had a stress element, and you knew what all these stresses were, this sigma x and so forth, and sigma y, sigma x, sigma y. And you know, if you knew what all these shear stresses were, tau, x, y, etc. What they did was they looked at a piece like that. Actually, it's a three-dimensional piece because remember, this thing is really it's like a sugar cube. It's got 3 dimensions. It's got 3 dimensions. So it kind of goes like that. they're looking at this kind of a wedge-shaped thing. Here, I'll try to color that wedge-shaped thing for you. There's a picture of it on page 451, only they didn't make it 3D like I'm trying to do. Can you visualize a kind of a wedge-shaped solid like that? Now, some of the forces on that wedge, I'm saying the word wedge, kind of like a doorstop. You know, doorstops kind of look like that, don't they? The sum of the forces have to be zero. Now, you can figure the force on this back face. See, force is equal to stress times area. So you can figure the force on that back face going that way. You can figure the force going down on this one. It's just the stress times the area of this bottom. Here, I'll try to draw you what the bottom looks like. Some hidden lines there. That bottom has an area, and if you multiply it by the stress, you can get the force going down. And also there's shear stress. See, there's a shear stress going down on this back face, and if you multiply it by the area, you'll get a force going down. And you see this shear stress going to the left. If you multiply the shear stress times that area of that bottom, you will get a force going to the left. Well, the sum of all these forces has to be zero. And so they break it into X and Y components, and they come up with the shear, the normal stress in the X prime direction. And they come up with the shear stress in the X prime, Y prime direction. They go through all of these trigonometric sine and cosines there, which I'm not going to do because we don't have enough time. And here's the result. We have a result. The result is called the stress transformation equations. They're on page 451. And they go like this. Come on now. Let me try a different, maybe a different one will work better. I don't know. Let's try that. This sometimes this blue one works good. Okay, so these are called the stress transformation equations. The stress, and here they are. I skipped the derivation because I was too lazy to, well, we don't have enough time for one thing. The stress in that rotate, see you rotated, you're looking inside the piece, is equal to I'm going to have to sacrifice some space here, but you can read it. It's in your book. Remember, we rotated at an angle theta. Well, when you do the derivation, it comes out 2 theta in the derivation. There's the formula for the normal stress at a rotational angle of theta. And they also have an equation for the shear stress when you rotate the angle. And there's your formula for your shear stress. Your transformed shear stress, looking at it from a different rotated angle, theta. Gee, I hope that shows up on your screen there. They're called the stress transformation equations. And we could do, let's do an example. Here, we'll do an example. Let me find one that I like here. Okay, here's one I think will be all right. Let's suppose, make a little room right in here. Let's suppose you had a stress element. After you've done all the work that we've learned in this class, your free body diagram, your equations, your stress element, and you come out with a stress element that looks like this. Ooh, hey, that's writing pretty good. And this is, that's your Y, your normal stress in the Y, and that one's compressive, isn't it? Of 2, we could say they're KSI, I suppose. And so you'd have to have, going that way, the same amount. And let's say this is 6. KSI. Of course, you'd have to have 6 doing that. And let's say this is the shear stress is 3 KSI. Okay, great. Well, then it's just a matter of picking an angle and trying it out. If you rotated this I'm going to rotate this. I'm going to rotate this an angle of 18.435 degrees. Now there's a reason for that, because I figured out that's where you get your maximum normal stress. We'll just do the normal stress right now. Never mind the shear stress. But see, 2 theta turns out to be 3687. See, there's method in my madness. And so we're going to plug this in. And it turns out that if you rotated this 18 degrees, which would be about like, it's not that big a rotation. You see that the amount that we rotated it counterclockwise is about 18 something degrees. And it turns out that that's where you have your maximum normal stress. Now I'll show you. Here we go. We're going to find the normal stress at that rotation. And it's going to be, well, we know what these are. This is 6. Now wait a minute though. This is not +2, it's a -2. It's 6 plus a minus 2 over 2 plus 6 minus a minus 2 over 2 cosine 3687 when you double it plus 3 sine of 3687. I want you everybody to plug that in their calculators into this stress transformation equation. And we're going to get the stress. What we're going to get is this normal stress on the rotated element. Go for it. You can do it. Okay, I got an answer. I wonder if anybody's got that yet. Let me go to my friend Mohammed. Unmute and say hello to me, Mohammed, please.
Hello, sir.
Mohammed, did you figure out this normal stress in the rotated? What do they call that? Stress element?
I'm working on it. Give me just a minute.
Yeah, take your time. Others are probably working on theirs too.
Okay, I got 6.599.
Do it again, Mohammed. It's not right. Here, let me help you. 6 minus 2 is 4. 4 divided by 2 is 2. 6 minus a negative 2 is 8. 8 divided by 2 is 4. Cosine of 36 is 0.8 plus 3 times the sine of 36, which is 0.6. Put that in your calculator and do it again.
— 6.6.
Nope. Here, I'll write it better for you. 2 plus 3.2 plus 1.8. Put that in your calculator and try it again. Hey, I like it. It's 7. Now, did anybody else that got 7 say, uh-huh?
Mm-hmm.
Yeah, there's one. Yeah, there's one. Interesting. We have just discovered that there's a internal normal stress. It's at a different angle. It's equal to 7 KSI. Well, you know what? That's bigger than 6, isn't it? See, what we're after here is the maximum stress. And you might think, looking at this thing, that the maximum normal stress is 6. Now that's tensile, this is 2, that's compressive, but I don't see any 7 on there. But it turns out that the maximum normal stress is 7. Interesting. We could also do the same thing with the stress, not the shear stress transformation equation. But you get the point. If you're after the maximum stress, it might occur at a different orientation. See, this is a different orientation. This has been rotated 18 something degrees, and it's got more stress on it. Now, if you take those two equations and do some algebra, which they do, I'm gonna skip that and get right to Moore's circle because it's gonna be fun for you. You'll love it. But I'm gonna show you where this is in your book on page. Yeah, there we go. On page 469. On page 469, can you read my writing? I hope you can. Page, yeah, there you go, 469. They have the shear stress equation. I erased it a little while ago. But it goes like this. Now what happened to it? Oh no, I lost it. Okay, let me find it again here. There it is. Now I hinted to you guys where they got these equations. They solved for the sum of the forces equal to 0 on your stress element. And they got these equations. I told you the page, you could read it for yourself. And then a guy named Moore came along and he did some algebra on these equations. What he did was he squared both sides of the equation. He squared them and he added them together. Well, actually what he did was he moved this term over here on the left-hand side. He made this a minus and put the equal sign here. And then he squared that, he squared this, he squared that, he squared this, and he added them together. And when he got through, what he had was this here. Remember, he squared that. And then he added this. And then he squared all of this, and he squared all of that. And he added them together. And now the marvelous thing happens is that whenever you have in algebra the sum of two things and you square it, you all know you get a squared plus 2ab plus b squared. Remember that from when you were all younger and better looking? Well, we have the sum of two things here and the sum of two things there, and when you square them, you get these middle terms. Well, these middle terms drop out. It's amazing. They go bye-bye. And all you're left with is the square of this term plus the square of that term. You know what? That's got a cosine of 2 theta squared plus sine squared of 2 theta. Does anybody know what the sine squared plus the cosine squared is equal to? Sine squared plus cosine squared is equal to what?
1.
It's equal to 1. It's equal to 1. How interesting. And so, the same thing here. When you square this and you square this and you add them together, here's what you'll get. You'll get a tall xy squared times 1, because sine squared plus cosine squared is 1. When you get all through, what you have on the right-hand side is this. Now that may not look important to you guys, but that's the difference between geniuses like Moore and the rest of us. He looked at this and he said, hey, you know what? That's the equation for a circle. Let me refresh your memory from when we were much younger and better looking. An equation of a circle that you learned in school. Does that ring any bells? Isn't that the equation of a circle? Let me call on somebody here. Brian, unmute and say hi.
Hello.
Hey, Brian, do you remember in probably high school that's the equation of a circle?
Yes, sir.
You actually remember. You're not just saying that to make me happy. You actually remember it.
Yeah.
Yeah, good for you, Brian. Well, see, here's your X, here's your Y, and here's your R. There's your R. And that's the equation of a circle. Now, this is the equation of a circle, only they've moved the circle over. It's not centered because they have an X, they have an X minus some distance, I don't know, call it A, that'll work. Come on now. Yeah, there you go. And see what that is, it's a circle that's been moved over a distance A. But it's still got a radius R. This is still X, this is still Y, but it's not centered. It's not centered. Can you read my writing? Dang, these dang pens. See, they scooted it over like that. That's what we got here. But the center has been scooted over, and you see this whole thing right here? You know what this is? That's equal to the radius squared. Well, it's quite an accomplishment he made. And now I'm going to show you how to do the Moore's circle. Need some room though. I'm going to have to erase some stuff so that we can show you this. Okay, now here's how you do Moore's circle. They have a step-by-step plan for doing it on page 471. They have Moore's circle step by step. It's like a recipe. It's like a recipe for making bran muffins, okay? You put the egg in, and then you put the milk, and Then you put a little oil in there or whatever, and you stir it, preheat the oven. You know, it's just a recipe. Here's what you have to do. You have to make your normal stress and shear stress axis. Let me do that. Dang these things. Let's try this one. Okay, now this is going to be the normal stress axis. Ooh, that looked good. And this is going to be the shear stress axis. It's kind of weird on this Mohr's circle, but the shear stress axis goes down, and the normal stress axis goes to the right. And what you do is, you see that 6 there? We got to measure 6. So I'm going to use inches, I think. Inches will be fine. Come over here, 6. I don't know if you guys can see this, but I want 6 inches. And then you see that 3 KSI going up. Well, going down is plus, so we got to go down 3. In order to understand that, I would have to derive. This is your anchor point. I don't know, call it point A or something. A for anchor, how's that? You know, they have anchors on ships, right? They throw the anchor off, and that's where the ship stays, right? That's a pretty important thing. Big old heavy anchor. That's your anchor point. Now let's look at this too. Well, that's compression. Well, compression is negative. So going to the right is plus, going to the left is is negative. So we're going to go to the left too. Now, if you went down 3 on this one, you have to go up 3 on this one. These directions are all in your book. Come on now. There we go. They're all in your book on page 471, the recipe for Mohr's circle. Then you connect the dots. Here we go. I'm going to connect these dots. We have just found the diameter of our Mohr's circle. Do you remember this was at 6 and this was at -2? That makes 8. So that makes this 4. That makes this 4. This is 3. This is 3. This is 5. And this is 5. We have a circle of radius 5. So here, let me draw it for you. I'll put some marks here at 5 so I can try to draw a nice circle. It's got a radius of 5. Now, I want you to be making some more circles for me for homework. I gave you some problems on, it's in content. Now here we go, I'm going to draw these for you. Here goes. We are drawing, yeah, there it is. We are drawing the Mohr's circle now. Ta-da! We have just drawn the Mohr's circle, and we can find the stress, normal and shear stress at any orientation whatsoever. But what we're interested in most is the maximum. Now, the maximum occurs right here. That's your maximum normal stress, and we can figure out what it is. Because if this is 6 and this is 4, then that means that's 2. The center's at 2, And if the radius is 5, that means this is at 7 KSI. Guess what? That's your maximum normal stress. Now, all angles are measured from the anchor point, and angles are always measured positively from counterclockwise. But you got to understand now, this is 2 theta. Since this is a 3, 4, 5 triangle, that means that 2 theta is 3687. You memorized the 3, 4, 5 triangle. I told you to a long time ago. And so theta is half of that, which is 18.435 degrees. At that orientation where you rotate it, you get your maximum normal stress of 7 KSI. Now the maximum shear stress is down here. That's your maximum shear stress. And we could figure that out from the stress transformation equations, or you can just get it from Moore's circle. It's just equal to 5. That's the radius. It's 5 KSI. We should plug that in and show you. Here, let me find the shear stress equation, and we'll plug it in and show you. I keep losing these equations. Let me dig around here and find them. Here they are. Okay, your shear stress in the rotated stress element is now we're going to plug in our numbers. Now we know what sigma x is, it's 6. And we know what sigma y is, it's -2. So it's 6 minus a -2. Well, that makes 8. Over 2 is 4, so you got -4 sine of 3687. Hey, can I help you? Hey, bud.
I was telling you, Brad,
Oh, give me a hug. Give me a hug.
there should be a package for you today.
I hope so. Now, where are you going?
At Hannah's house.
Oh, yeah. Yeah,
If
that,
there's a package, will you bring it in?
yeah, sure. No, I'm going to leave it out. In fact, I might kick it out in the street.
It might come during your class.
Yeah, okay. Hey, bye-bye.
Bye-bye.
Now, let's see, where were we? And I got lost here. Oh, yeah, +3. See, the shear stress is 3. I need a little room here, though. Gosh, I'm running out of room. We'll just make room. Hey, we'll make room. Plus 3 times the cosine of 3687. Okay, now I want you to put this into your calculator. I know you can do this. Did I get the right equation? Yeah, I think that's right. Okay, plug that in and see what you get. Go ahead. I'm going to do it. Oh, no, wait a minute. wait a minute. I goofed up. You get you get 0 when you plug that in, because see, to get down here, you've got to go this way. This angle, all angles are measured from the anchor point, guys. So this angle is not 3687. It's minus 5313. My mistake. Minus 53. All angles are measured from here at the anchor point. Going clockwise is negative, and that angle, the 2 theta there is equal to 5313. Now, you plug that in, please, and see what you get. I goofed up. Okay, here goes. Well, I got an answer. I got 5. How about you guys? Well, that is the answer. It's 5. So Mohr circle worked. Did anybody else get 5? If you got 5, say uh-huh.
Mm-hmm.
Yeah, there you go.
Uh-huh.
We might have time for one more if we hurry. But that was a lot of fun. Now you're going to be doing some of these, so maybe we better try another one so that we can feel good about it. Okay, I'm going to erase all this unless you have a comment or question. All right. The topic today is Mohr circle. It's in chapter 9. And we're going to do another one now. Now here's your stress element. Now to get this, remember, you got to jump through a whole bunch of hoops to get this. See, you know what that is? That's your normal stress in the x direction. And then the shear, you know what that is? That's your normal stress in the y direction. And then your shear stress is 6. Let's say after all the work that you went through, you came up with a stress element like that. See, this is 4 KSI. Hope you can read my writing. There we go. Shear stress is 6. Normal stress is 20 in the x direction. Now we're going to do the Mohr circle. And I can tell you what the maximum stress would be on this stress element. So first, remember the rules. Follow the step-by-step foolproof plan on whatever page that was I told you guys. And then make your normal stress shear stress diagram. Okay. Okay, now, see that 20? You come over here, 20. Uh-oh. I can't go 20 inches. That'd run off the board there. I could use 20 centimeters, though. That might work. Let's do that. That puts me right here. There. Now this is at 20 KSI. Now this here is 4, but that's tension. So you don't go compression, you don't go negative, you go 4. I'm using centimeters, so let me do that. There we go. This is at 4. Now remember, according to the directions, if you go over 20 and that goes up 6, you got to go down 6. So let me go down 6. Here we go. There's 6. Now you realize you can get all of this information from those stress transformation equations. But this is pretty neat. You can get them from Mohr circle too. Now this, if you went if that's 6 and you went down 6 here, then you go up 6 here. So I'm going up 6. Here we go. Ta-da. And this is your anchor point right here. That's your anchor point. Hope you can read my writing. Now we're going to connect these and we'll have our diameter of our Mohr circle. Here goes. Oh, gee, it doesn't. These pins, I'm not happy. That's a little better. See, that's the diameter of your Mohr circle. Now, if that's 20 and that's 4, that's a difference of 16. Well, this should be 16, is it? Yeah, pretty close. Yeah, pretty close. So that means this is 8, this is 8, this is 6, that's 6. You know what? We have another 3, 4, 5 triangle, guys. Only it's a 6, 8, 10. See, if you have a 4, 3, 5 triangle and you double it, you get an 8, 6, 10. I want you to be able to recognize 3, 4, 5 triangles. Okay, and so that doesn't look like 10. That's more like an 11 and a half. I must have done something wrong. Now, just a minute here. Oh, that's my problem. It's more like that. The 20 should be right there. Oh, well. I think I'm a half a centimeter off, but you get the idea. Now, oh gosh, I have 1 minute left. Here, let me just draw this Mohr circle and we'll find the maximum stress and we'll have to adjourn. But it's been fun. Can you see that this is going to be the maximum stress right there? And I can tell you what it is. Now, let me think. If this is 20 and that's 8, that makes this 12. See, 4 and 8 make 12, yeah. And if the radius is 10, and that's 12, you know what? The maximum normal stress is 22 KSI. It's not 20, it's 22. And I can tell you the angle it happens at. All angles measure from here. The 2 theta is equal to 3687. And so the theta is that 18 something that I can't remember. 18.4 something. Well, there you have it. There's no class on Wednesday. Wednesdays, Thanksgiving starts Thanksgiving holiday. So I won't see you guys till, well, I'll see you Monday. You know, when we meet next Monday, that's the last week of school. It's sad because I know you enjoy this. Okay, last comment or question. I'm going to push this red button.
Mr. Griffin, how you get the 22 KSI?
Oh, thanks for asking. If this is 12 and this radius is 10, 10 plus 12 is 22. See, the radius is 10. You've got an 8, 6, 10 triangle. It's double of 3, 4, 5. And so if you take 10 and add it to the 12, you get 22. Did that make sense?
I guess, yes.
See, this has got to be 12 because going to here is 4,
Mhm.
and that's 8. 8 and 4 is 12. See,
Okay.
going to here is 20. 20 minus 8 is 12.
Yes.
Well, I tried, but I got to go, guys. Bye-bye, students.
Bye.
But
Bye-bye.
Professor Griffin, did you
Yes.
have a minute to talk with me?
Yeah, I'll talk to you. I don't want to embarrass you, though. How do we talk without... Can you talk with others listening in?
Yeah, it's all right. I was extremely sick last week with COVID, like
Oh,
the full
brother.
body aches, the loss of taste and stuff. And
how awful.
I wasn't in your class last week at all. I wasn't able to attend. And so
Look at the YouTube. Look at the YouTube.
well, yes, sir, yes, sir. But I was gonna wait until the weekend to take care of all the work, and I had missed where test 3 was due on the Friday instead of the Sunday,
Oh,
because the first 2 tests were due on the Sunday. So I thought I would be
Yeah.
fine if I.
well,
It's
here's
completely
what
my
I'm going
fault.
to do. Here's what I'm going to do. If you read the syllabus, we'll replace that missing test 3 with a score on your final. Do real good on the final, and I know you will because I'm preparing you well, and you won't miss it. You won't miss out on a thing.
Yes, sir. Okay.
That's what we're going to do.
All right.
Do good on the final, and you'll be fine.
Okay. Awesome. Thank you very much. I appreciate it.
Thank you. Bye-bye, everybody.